This is lecture 20 of game theory course. My apologies. The lecture 19, at the end of lecture 19, the camera stopped abruptly and you would be surprised what's going on. I was surprised too. But anyway, I'm not good at this technology, so instead of taking every lecture in the previous lecture, I would rather continue. And I'm not good at editing, so I don't know how to connect those two lectures. So sorry for the inconvenience, but I will start what just stopped in the previous lecture 19. Okay, where were we? We were here that Professor A sent the TA so that the TA would, with the order that TA should never choose project 2. He is rather allowed to do no project, but never project 2. So this project 2, the yellow one, is kind of the bridge behind which Professor A has burned. Okay? From Professor B's point of view, this project 2, which is kind of retreat or withdrawal of Professor A, is gone. Now he has to choose between project 1, which is Professor B's second choice, or no project 0. So 5, 0, 5 is better. So by sending TA and one of the three options, project B, Professor A has get rid of. Burn the bridge, burn the strategy. That's how he ended up getting 10 million instead of 5 million in this project. First or second, we just have looked at sometimes it is good to be the first mover, like this burning the bridge behind. So if you're the second mover, they want to burn the bridge behind to be a first mover. Or sometimes it is good to be the second mover, like the farmer and lion, because the second mover promised something to the first mover, but when the first mover did that, like pulling out all the teeth, the second mover say, I lied and betrayed him or her. Okay? So, I already told you in the second mover advantage case, you would say, oh, please, you should first. You act first. North Korea said, please, America, help us first. Then we'll get rid of our nuclear missile. America said, no, no, no. You get rid of your nuclear missile first. Then we will help you economically. Come back to the burning the bridge behind. By getting rid of your own choice, you can be the first mover. Okay. One another very often frequent case using this burning the bridge behind is the incumbent versus entrant. Incumbent is someone who's already in the market. Like you are the only bread company in a village, in a city, you're an incumbent. You would be entrant if you are not making bread yet, but thinking about getting into that city, then you are in the position of entrant. If you are an incumbent company, you always worry about the entrant. You are making a lot of profit in this city, which means other companies want to enter. If Professor Han is making a lot of money teaching game theory, then Professor Kim think, oh, maybe I should join and teach another game theory so that I can make money too. Fortunately for me, I'm not making money at all, so nobody want to teach game theory. No, there are two other professors here, but anyway, it's not very popular. Incumbents. What would the incumbent do? Think about that. If the entrant really enter and say, oh, you're selling 100 bread a day, why don't we divide it 50-50? Or we can fight ourselves to death. Then now you are selling 100 bread and making a lot of profit. When your entrant threat you, are you going to make half of the profit, like 50-50 bread, dividing it up, divide the market up? Or are you gonna fight the entrant so that either one of you will die, bankrupted? Now, bankruption is a really scary thing for the businessman. So I wouldn't be surprised if the incumbent bread company owner would say, okay, let's divide 50-50. That is like when your enemy burning the bridge, you just surrender. Okay, I'll give up, kind of thing. However, there's one thing you can do is you said, okay, I'll give up and let's divide. You cannot do that. Why? You invest a lot of money in the bread, so much over investment. So because of the over investment, 100 bread would be minimum. Okay, if you sell less than 100, you have like 2-3 factories of bread. And if your production is less than 100 bread, there's no option you'll be bankrupted. Once you do that, when the entrant come to you and say, oh, let's divide half and half, and you would say, okay, I am making 100 or something more, but then if we divide up, you got 50, I got 50. But then, because the minimum production level for me is 100, it's the same for me. If it's less than 100, I'll be bankrupted anyway. So if you want to fight, I'll fight. But then it's not possible for me to divide the market because I am over-invested. I have too many factories, and if they do not produce enough bread, I'll be bankrupted. Okay, so kind of this incumbent company, by over-investment, get rid of the option to share the market. So the entrant option is, okay, sharing the market, dividing the market is now impossible. So entrant either stay out, don't enter, or enter and fight to death. Once again, fight to death, bankruptcy is such a scary thing. Probably the entrant would not enter. Okay? Commitment mechanism is related to the case where second mover has advantage, like the central bank and the labor union. The labor union is the first mover all the time, and the central bank is the second mover. The central bank would say, oh, we are not going to print out more money so that we are not going to cause inflation. So please do not increase your wage too much. If that's credible, the labor union would be willing to freeze their wage this year because corona, situation, everything. However, they might never believe that. Say like, oh, if we, even though you say right now there's no inflation, once we freeze our wage this year, you are going to print out money more, break your promises, and cause inflation because that fits your profit. It would be very nice if the central bank can commit itself, and which means a promise that can never be broken, so that the labor union believe the central bank perfectly. Actually, the central bank is a kind of commitment mechanism, we say, because they are not politicians. Their job description is worry about inflation, not so much about the recession and job creation. So they would say, okay, we care a little bit about the unemployment, but we care more about the inflation. So even though the politician wants inflation, we decide the labor union that no inflation, so we are not gonna print out money, kind of thing. This is not very easy. I mean, in order to commit, we have this huge central bank, huge building, 1,000 people working in it, kind of thing. And all this is for what? Make a commitment. The central bank is not under the order of the president. So the president might say, I need to vote for the next election. The central bank chief would say, oh, you have an election, good luck, but we do not receive your order. Okay? That is commitment. Okay, the next topic is a little bit complicated. So I hope you are in your best study shape. It is about non-equilibrium path. You already knew it, but then let's formally explain this. Think about the next game. Player 1 and player 2. But player 1 choose twice, then player 2. Player 1 either choose SA strategy or SB. If player 1 choose SA, the game stops immediately and player 1 gets 2 payoff, player 2 gets payoff 2. If player 1 choose SB strategy, then player 1 and player 2 play this game. Because of the circle around player 2, it's kind of player 1 choose, but player 2 cannot see player 1. So virtually it's the same as simultaneously choosing between player 1 and 2. If player 1 choose S1 and player 2 choose T1, it's kind of player 1 wins. So player 1 gets 3, player 2 gets 0. If S1, T2, this time player 2 wins 3 and player 1 gets 0. If player 1 gets S2 and player 2 choose T2, player 2 gets 3, player 1 gets 0. If player 1 choose S2, player 2 choose this is T1, T2, T1, T2, I'm sorry. Not 3 and 4, 1 and 2. So many typos. But anyway, if player 2 choose T1, it's 0 and 3. Player 2 choose T2, it's 3 and 0. Okay, I have to rewrite this. Okay, so here, if you look at this, player 1 choose S1, it might get 3 or 0. Player 2 choose S2, it might get 3 or 0. Player 2, this is T3, not T3, T1. T4 is T2. Player 2 choose T2, it may get 3, but T2, it may get 0. T1 may get 3, T1 may get 0. So it's like there cannot be a pure strategic equilibrium in this game, player 2 and player 1. When player 1 chooses SB, this has the mixed strategy equilibrium, where this is a simple game, like the strategic form S1, S2, T1, T2, 3, 0, 0, 3, 0, 3, 3, 0, something like that. And then the Nash equilibrium, mixed Nash equilibrium in the game is playing S1, S2, T1, T2 with probability half and half. And please try yourself. And then the expected payoff would be 1.5, 1.5, because both player 1 and 2 get 3 with probability 50%, 0 with probability 50%. So expected payoff, the average would be 1.5. So what would happen? Player 1, if he chooses SB, he would play a game where the expected payoff would be 1.5. Or he stops immediately by choosing SA 2. 2 is better than 1.5, so player 1 stops. That's what we expect to be happening in this game. Make sense? Hopefully so. Then the subgame perfect equilibrium would be player 1 choose SA, SB, S1, S2 with probability 1, 0, half, half. It is understandable SA probability is 1, SB's probability is 0. But then I said S1's probability is half, S2's probability is half here. But then, because player 1 choose SA, player 1 would never have a chance to choose between S1 and S2. Same as player 2. You can choose T1, T2, T1, T2, but then if player choose SA with probability 1, it will never come to the SB. So whatever player 2 choose would never be played. But then, it's not because I wrote it wrong. This is the subgame perfect Nash equilibrium. Why? If you look at this, or look at this. This we call non-equilibrium path. Okay? Equilibrium path is where the play really happening in real time. So SA. In this game, player 1 choose SA and game ends. So we can observe this. That is equilibrium path. In equilibrium, what can we see? SA, period. So we call that equilibrium path. On the other hand, choosing SB, that would never happening in this game, in this subgame perfect equilibrium game. This path, we call non-equilibrium path, would never be really played in the equilibrium. Whether it's subgame perfect equilibrium or Nash equilibrium, whatever. So this non-equilibrium path is something we would never observe. However, still, once again, this is T1 and T2. However, why, if someone asks, why did player 1 choose SA and get 2? Because there are something like 3 here. Why player 1 gave up 3 and get 2 instead in the equilibrium? The reason is, in this non-equilibrium path, if player ever had choose SB, even though he chose SA, if he had chosen SB, what would be happening? Half, 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 half. He would get expected payoff of 1.5 because they would randomize S1 and S2 half and half, T1 and T2, T1 and T2 half and half. As a result, this. So, even though this non-equilibrium path is not really happening, this, what could have happened in the non-equilibrium path is the reason why the player choose the equilibrium path. The game theory demands the whole story, not just I did that. We want to have, why did you do that? Why didn't you go to Mokpo, but why did you go to Busan, which is 2 cities in Korea? And it's not enough to say, oh, I started from Seoul, I came to Busan. I arrived in Busan. But you have to explain why I didn't go to Mokpo, why didn't I stop at Daejeon, why didn't I went to Incheon airport. So, what might have happened, but you didn't choose, should have a reason. That is non-equilibrium path, and your answer should include that. Okay, that's why S1 and S2, T1 and T2, they will be played half and half, half and half. It will never be played, but because they play half and half, half and half, the expected payoff from SB would be 1.5. That is why player 1 didn't choose SB. The probability of SB is 0. On the other hand, SA, the probability would be 1. Okay? Keep in mind, don't forget to mention the non-equilibrium path. Here, S1, S2, T1, T2, even though SB probability would be 0. Okay, I hope you remember this game. At first, probably first lecture, first week this semester, I introduced as Ghost Subgame. But the formal name of this game is Centipede game. Centipede is a bug, very long and many legs. And that is why they use this name, not me, the original author of this game. They probably think this game looks like Centipede. This is extensive form game, but instead of doing this to the very long to the down, they do it on the horizontal. Basically, Tom choose go or stop. If he choose stop, game ends there. If he choose go, Bill has a chance. Bill can go or stop. If Bill stops, the game ends here. If Tom stops, Tom get 1, Bill get 0, but go and Bill stops here. Now Tom get 0, Bill gets 1. But if Bill choose go and Tom stops, Tom gets 3, Bill gets 0. But if Tom choose go, Bill stops, Bill gets 4, Tom gets 2, on and on and on. But if they go to the end, it's 5 to 5. Okay, what would be happening? What should we apply for? What kind of equilibrium concept should we apply for this game? Yes, you're right. The subgame perfect equilibrium, which means backward induction. The game begins from left side, but backward induction means we have to track down from the future, which is right hand side. What would Tom choose at the end? Go and 5, stop and 6. Well, he's a very clever guy. He would stop and get 6. Think about 6 million and 5 million. I mean, no brainer. You should get 6 million. Bill, of course, he can do the backward induction on what Tom would do. Unlike the lion of Aesop, Bill is a smart guy. Whatever Tom may say, oh, don't worry, I will go and you will get 5 million instead of 4 million, stop here. But then Bill said, come on, Tom, I know backward induction. You would stop because that will give you 6 million. If you go 5 million, you are my good friend, but I don't think you will do that to me. If you stop here, I'll get 3, which is less than if I stop here getting 4, so I'll stop. Tom here, know that Bill would stop by backward induction, and Tom will get 2 million, so he will stop here, get 3 million. Bill, if goes, nothing of the right hand side will be happening. Tom stops immediately, and Bill would get 0, so Bill would stop here. Tom, know that if he goes, Bill would stop here, getting 0, so why not? Stopping here, at least getting 1. Okay, so in this game, what do you expect to happen in subgame perfect equilibrium? Tom, stop, game ends. But how would you write down this subgame perfect equilibrium in the exam? Of course, if you say, oh, Tom stops immediately, period. Sorry, that's 0 point. For your information, once again, in this game theory course, if I ask you to describe something, the equilibrium, and you are half right or 99% right, your score would be 0. If you forget to mention the non-equilibrium path, if you just write down the payoff instead of the strategy, 0 point. Okay, so once again, be careful. Here, what should it be? Tom, stop, stop, stop. Bill, stop, stop. That is the subgame perfect equilibrium of this game. Of course, why 3 times? There are 3 places Tom choose. Stop, stop, stop means Tom stops here, Tom stops here again, Tom stops here. Bill stop, stop. Bill has 2 places to choose. Bill stops here, Bill stops here. So every possible choice, Bill and Tom both choose stop all the time. Of course, because Tom stops here, Bill would not get stop here. But, so this is non-equilibrium path. So here, except for the first stop Tom has chosen, the stop, 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 the 4 stops are non-equilibrium paths, which we will never observe. They will never have opportunity to do. However, if you ask why Tom stops? Of course, Tom stops, but why Tom stops? Because he can get something like 5 million or 6 million. The reason is Bill would stop. Why Bill stop? Tom would stop. Why Tom stops? Bill would stop. Why Bill stop? Tom would stop. So even though this is something weird, the non-game theorist student, now we know stop, 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 already had this big story. Because Tom will stop, Bill will stop. Because Bill stop, Tom stop. Tom stop, Bill stop. So, thinking all this, Tom just stopped and did the game. That message is in here. Okay, the most difficult question I'm going to ask, okay, that is find out Nash equilibrium of the game. Okay, there's only one subgame perfect, stop, 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 but is there a Nash equilibrium which is not subgame perfect? Okay, subgame perfect is one of the Nash equilibrium, but that means there are Nash equilibrium which is not subgame perfect. What would that be in this game? I'll give you just one example. Stop, go, go, stop, go. Which means Tom stop, Bill stop, but Tom go, Bill go, Tom go. If this is happening, the same thing happens as subgame perfect. Tom stops, period. However, how is it possible that Tom go, Bill go, Tom go here? In Nash equilibrium, the key point is, can you change your strategy and get better? Now, in this game, because Tom stops, Tom gets 1, Bill gets 0. From Bill's point of view, as long as Tom stops immediately, whether you change go here or Bill choose go here in this, look at this. Tom stops, Bill stops at first, and go, 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 go. If Tom stops first, from Bill's point of view, whether you stop and go, whatever you do here, it doesn't matter. Because whatever you do, game already ended and you get 0. So Bill cannot get better by changing stop, go to something else. Sorry, confusion. On the other hand, what about Tom? From Tom's point of view, what is important? Bill would stop here. When Bill stops here, Tom does not choose stop, go, he will get 0. So getting worse. Tom chooses something else while stopping at first. Tom stops, himself stops, he get 1. Whatever he does not matter. So here, as long as Bill stops at first, Tom cannot get any better by changing this. If he does not stop, his payoff would reduce from 1 to 0. So as long as Bill stops, Tom stops first, and the next doesn't matter because Tom stops and it wouldn't matter. It immediately becomes non-equilibrium path. As long as Tom stops at first, whatever he does later, whatever Bill does is useless because Tom stops, Bill gets 0, and then whatever he does, it remains to be 0. So surprisingly, stop, go is Nash equilibrium, even though this is not subgame perfect equilibrium because backward induction would say it's wrong. What about stop, stop, go, stop, stop, or stop, stop, go, something like that. So there are several Nash equilibria. Please think it by yourself, which is not subgame perfect equilibrium. Okay, this has been exam a lot of times. So please check. It's confusing and very difficult concept. See you next time.